Alright guys, so in the parallel circuits video that you've already watched, we set up everything to get to this point. In this video, our main goal is just to figure out what the total resistance is. So far we remember that the I total, the total amount of resistance or current in the circuit, is equal to the amount of current in each of the branches added together. So just a reminder, we'd add this current, and this current, and that would give us this total current that's here before it splits up. We also looked at how the voltage, it's almost as though each resistor is connected independently to the battery. So the voltage drop of the battery is exactly the same as the voltage drop over any one of those three resistors. So the voltage total, which is also known as the voltage of the battery, is equal at each location. Now what we're going to do is use Ohm's law, which we've already practiced a little bit. Delta V equals I times R, and we're going to see if we can figure out what we would have to do to get the total resistance. We know in a series circuit, that's where all the resistors or any of the circuit elements are in the same branch, so there's only one current. We know how to get that total resistance. We just add up the different resistance values. But on this one, we're going to have to do something a little different. So let's take a look. Alright, so I've got delta V is equal to I times R. That's my starting point all the time. And I know that this works if I'm looking at just one local point, like at one resistor, or if I'm looking at the total. So what I'm going to say here is I'm going to start with this idea, that the total current is equal to the current running through each resistor or branch, and we just add them up. Now I'm going to solve for I here at the top, okay, and I'm going to do, that would be equal to, so I would be equal to delta V over R. So now I'm going to plug in this expression, delta V over R, in for each of these I values. Okay, so what I'm going to end up with is delta V total over R total equals delta V 1 over R1 plus delta V2 over R2 plus delta V3 over R3. Alright, so what I did there was I just substituted in each I value with delta V over R. Alright, so now what I'm going to do is remember that delta V is the same in every single resistor, so the total voltage is the same thing as the voltage drop over the first one, or the second one, or the third one. There is no difference. So if delta V is the same in every term in the blue equation, then that means I can factor it out. I'm going to just factor it out, and that makes 1. Alright, so I'm left with now 1 over R total, which is what we're trying to find, is the R total, equals 1 over R1 plus 1 over R2 plus 1 over R3 and so forth. Now we want to solve for R total. Alright, so what I'm going to do is let's switch colors here. I'm going to keep those all together because that would just be plugging in the value of each resistance. Okay, and now I've got to solve for RT. So I could multiply by RT on both sides and then divide by this parenthesis on both sides. And what I'd find is that I have R total is equal to R1, 1 over R1, plus 1 over R2, plus 1 over R3, all raised to the negative first. Or, in other words, 1 over all of that. So this is the way that you find the total resistance for a parallel circuit. And that's why every time you add a resistor, so every time you add a resistor in parallel, the total resistance actually goes down, which is kind of strange, right? So the total resistance will go down when a new resistor is added in parallel. That's the symbol for parallel, right? So the total will drop every time a new resistor is added in parallel. So let's do a little quick example so we can see how this actually works. All right. Okay, so let's say I have a battery, resistor 1, resistor 2, I'll do 3, okay, and let's say that each resistance is equal to the same amount, so we'll put 2 ohms. Alright, so I'm going to make the battery 12 volts, just for kicks, and then what I want to know is, what is the total resistance? What is the total voltage? And what is the total current? Well, I already know the total voltage. That's probably the easiest one. That's just given, which is 12 volts. Now, the total resistance, I can calculate that using that formula I just derived. Let's see here. That'd be 1 over R1 plus blah 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 to the negative first. Alright, so let's plug in the values. So we say 1 over 2, because that's the value of the resistor, for the next one, for the third one, all to the negative first. So in other words, take all of that and divide it into 1. Alright. So let's do just common denominator here, which is already found, is 2. So I have 1/2 plus 1/2 plus 1/2. That should give me 3/2. That's to the negative first, which is basically saying the inverse of it, right? So if I did 1 over that, I would get 2/3, which 2/3 is approximately 0.67 ohms total. So this is so cool and kind of strange, is that the total resistance in a parallel circuit, the total resistance is smaller than any one resistor. So let's just look at one reason why that would be. Well, wait, let's first finish this one, and figure out the current. Okay, so I have this to begin with. Oops. Alright. So the 12 volts was given. I'm looking for I, and the R we just found was 0.67. So I must be equal to 12 divided by 0.67, which probably be actually easier to do with the fraction instead. And I find that we get, I think, 17 or 18. So let's do it. 12 divided by 0.67. Yep, so I get about 18 amps is my current. Alright, so you literally just have to do this every time. Even if they're different numbers, that's fine. You can just add them on your calculator as decimals, however it works for you. So let's just quickly look at a reasoning of why the total resistance is less than any given one resistor. Alright, so we're going to think of this analogy. There are 3 checkout lanes at the store. Okay, so you can either go here, here, or here to check out your groceries. But everybody starts in the same line. So they have, here's a line, and then you've got all these people standing in line, and your job is to, or when one of the tellers or the cashiers opens up, you go to the open one. So somebody could go to any one of them. But once you go through one cashier, one checkout lane, you're not going to go back through another checkout lane, right? So that's also a reminder of how we talk about high potential to low potential. So what's going to happen here is the current, or the traffic flow in this example, would be how many people are passing, say, this point right here in a given amount of time. Well, if you have really efficient cashiers, then people would just continuously be flowing through and you'd have a pretty high current. Now let's say one of the cashiers closes. Alright, so you can't go this way anymore. So this one's closed. Now, what's going to happen is the total resistance to the flow of people has actually increased. Now, these cashiers are like little resistors. Resistor 1, resistor 2, resistor 3. They're really branches, right? Options, paths that the electrons can take. So if I close one of them, if I get rid of a resistor, what happens is we're backed up more. So the current will drop because the total resistance went up. But now if I add so let's remove these lines. If I add this lane back, let me erase this. If I add this lane back, so I've added another resistor, okay, it's now opened another branch, and so the total resistance has dropped. The number of resistors isn't as important as the total resistance. So you can see that people would be able to go through a lot faster. If I were to open a fourth one, then the flow would be even better, right? And I'd have total less resistance. Whereas for a series circuit, it would be kind of as if the checkout lanes were arranged, the cashiers were arranged like this, which is stupid in general. So, because if I have all these people lined up here, you have to wait, even if the person in front of you is not done, and you have to basically check out at every checkout lane, alright? And so by adding another checkout, you're actually slowing it down, so you're increasing the resistance. That's for series, right? So adding a resistor in series makes the total resistance larger and the current smaller. Adding a resistor in parallel decreases the total resistance and makes the total current bigger. I hope that video helped, and use some of the notes from this video to complete the daily practice questions.